We'll now look at partial fractions, what they are, and how they can help us with integration. The kind of idea is if I have this fraction 1 over x minus 4 plus 2 over x plus 2. We know how to add fractions, and when we do, we would get 3x minus 6 over x minus 4x plus 2. And so far, anytime in math, this is probably what you wanted to do. However, if I look at the right-hand side of this, if I were to try to integrate this, this would be extremely difficult to do. And as of right now, we don't have any methods to do it. However, on the right, it's much, much easier. So now the idea is to go the other direction. I have this complicated fraction that looks like something on the right, and I want to move it to what this looks like on the left so that we can more easily integrate. And we'll look at the first case. There are several different cases in partial fractions, and the first one deals with simple linear factors. Our first step will be to factor the denominator, and when we factor it, we should be able to factor it into simple linear factors. Therefore, everything should factor into linear terms, and this simple means that nothing is repeated. We don't have anything like an x plus 2 squared. And so this is the first case we'll look at, where when we factor, everything factors and each one of those terms is unique. The next step is we'll set up these fractions to look like this: a over x minus r1 plus b over x minus r2. Essentially, whatever we factored the denominator in step 1, each one of those terms should get its own fraction at this step with some kind of variable on the top. We'll then take step 2, set it equal to our original function, and then solve for these unknowns on the numerators. And we'll do a couple of examples to demonstrate this process. Here's our first example. We want to integrate 3x minus 11 over x squared minus x minus 6 dx. So we're going to start with the partial fraction decomposition. And the first step to that is to factor the denominator. And we can see that the denominator will factor into x minus 3, x plus 2. Now that we have that, we set up a fraction for each one of these terms. I have a over x minus 3 and b over x plus 2. From there, we're going to multiply this entire thing by the denominator. Anytime we have an equation with fractions, multiplying the denominator is usually the first step. On the left, this becomes 3x minus 11. On the right, the a over x minus 3, the x minus 3 terms cancel. I'm left with a times x plus 2. And with my second fraction here, the x plus 2's cancel. I'm left with b times x minus 3. And the idea now is that we need to solve for a and b. One of the ways to do that is to realize that this equation should be true no matter what values I stick in for x. So we can choose some good values for x and then figure out what a and b need to be. Ultimately, you can pick any values for x to stick in to try to find a and b. However, the most helpful ones are ones that make these terms 0. We'll start with x equal to negative 2. On the left, that would be negative 6 minus 11. And on the right, we have a 0 and then a b times negative 5. So negative 17 is equal to negative 5b. So b is equal to 17 over 5. We could also let x be equal to 3. On the right, we have 9 minus 11. Or on the left, we have 9 minus 11. On the right, I have a 5 times a and then a 0b. So negative 2 is equal to 5a, which means a is negative 2 over 5. And so now we can set up our integration. Here's what we have now that we have done our partial fraction decomposition and substituted it back in. And we can integrate these pretty well. The constants on the numerator pull out, and then this bottom term is going to be ln of x minus 3. The second one I have 17 over 5, and this will turn into ln of x plus 2 plus c. Here we have another example. When I try to factor the denominator, I can start by pulling out an x, and then we can factor into x minus 2, x plus 1. And we can now set up our partial fraction decomposition. Each term on the left should get its own term on the right. So I have an a over x, a b over x minus 2, and a c over x plus 1. And then we're going to multiply through by the denominator. On the left, I'm left with 3x squared minus 2x minus 2. On the right, I have a x minus 2, x plus 1, plus bx, x plus 1, plus cx, x minus 2. And once again, we can choose some good values for x. If we let x be equal to 0, on the left I get a negative 2, and on the right, the a term becomes negative 2a, and the b's and the c's cancel. So I get that a is 1. Another good value would be to let x be equal to 2. On the left, 2 squared is 4, so I have 12 minus 4 minus 2. On the right, the a cancels, the b becomes 6b, and then the c term cancels. So this is 6 equal to 6b. Therefore, b is also equal to 1. Finally, I could let x be equal to negative 1. On the left, I'm left with 3 plus 2 minus 2. On the right, the a term and the b term cancels, and I'm only left with the c term, which is 3c. So we get that all three values are 1. Going back to our original integral, the integral of 1 over x is ln x. The integral of 1 over x minus 2 is ln of x minus 2. And the integral of 1 over x plus 1 is ln of x plus 1. And then plus c.